Good morning, guys. So today is your fourth lecture, and we'll start the magnetic materials. So till now we have seen the dielectric materials and the properties of dielectric materials. So magnetic materials are also the underlying physics is kind of similar, but when I'll discuss, you'll understand the difference and the similarities. So the word magnet, it has its origin in the from magnetite, which is a form of iron oxide. So I can just write it down. So magnet has its origin in a magnetic material known as magnetite. This is a form of iron oxide, or people also call it lodestone. Let's say iron oxide or lodestone, which you might have heard we use in magnetic compass. All right. So first, this lodestone, it was mined in a province in Magnesia, actually. So there, where the name originated. So it is believed that among all the other minerals, in Magnesia, so the magnesium carbonate was white, the magnesium oxide was manganese oxide was brown, and magnetite was black iron oxide. So the magnetite was probably the first material known to be magnetic. So just write this statement also down. So magnetite is probably the first material known to be magnetic. Okay, more or less, I could say that most of the materials that you see around, they are magnetic, meaning they respond to magnetic field in some fashion. So when I say magnetic, means they respond to magnetic field. In some fashion. What's that pattern is, we'll see whether it gets attracted, it gets repelled by the magnetic field. We'll see what happens. But if they respond to the magnetic field, they are called magnetic. So in this chapter, we'll define different types of magnetism. Something like ferromagnetic, ferrimagnetic, these kind of material which are similar that we saw last time. Ferroelectric materials, okay, but this time it's magnetic field which is going to play the main role. We will also briefly mention there is other class of material which is called multiferrics, which are really important because they are used in they have some two or more switchable properties, meaning they behave like a ferroelectric as well as they behave like a ferromagnetic. So we'll briefly see multiferrics as well. The origin of ferroelectricity and ferromagnetism, it's actually different. Ferroelectricity, as we saw, it was because of electric field, and ferromagnetism, all the properties will be because of the magnetic field. That was the let's say major difference also. And Apart from that, these magnetic materials are used in different technological aspects, magnetic tapes, storage device. So it's better to understand what is the basic physics, how the this behavior appears in different system. What is the phenomenology behind this property? So the origin, as I said, of magnetic and dielectric behavior is quite different. Okay, because the magnetic one, it's related to the spin motion of electron. However, the dielectric one was related to the non-uniform distribution of the electric charge, right? So I'll just write it down. So the um, physical origin of magnetic and dielectric behavior are quite different. Because the magnetic one, it is related to the spin motion of electrons. However, the dielectric, it's related to the non-uniform distribution of electric charge. Okay, so this is the difference in origin. Okay, so now let us see the origin of magnets. Most of the atom, they are magnetic nature, meaning they respond to magnetic field in some way, um, uh, in some specific manner. So the origin of magnetism, it lies in a very basic principle, which is moving charge. I'm pretty sure you have learned it before, but let's see it again. So whenever we have a moving charge, meaning we have electric current, so it produces a magnetic field. If you remember, um, that, let's say this is a current carrying wire. Okay, so let's say wire, current carrying. Then if you put a compass next to the current carrying wire, the compass needle, it gets deflected, meaning there is a presence of magnetic field in the system. Okay, so that's the really basic or simple way to see the origin. And the connection between the electrical current and magnetism, probably, I think Hans Oersted was the first who discovered that when you put a compass needle close to a current carrying wire, it deflects in a perpendicular direction. So let's say if we have a current carrying wire I like this, and the area of the loop of the loop is A, then the magnetic moment, which we will denote like as mu. So mu is equal to more or less it is a product of I times A, IA. Okay, so I can show it like this. It's a magnetic moment induced by a current loop. So let me just say, just write it down, by a current loop, which is product of the current and the area enclosed by the loop. So the magnetic moment, it's a building block of magnet. Conceptually, it's similar to the dipole moment, which was the building block for, let's say, a dielectric material. Okay, so this magnetic moment is the building block of the magnet, similar to dipole moment. Remember, dipole moment was charge time the distance, q time x, that we defined. So the dipole moment of dielectric materials. And the unit of this magnetic moment, mu, unit of mu, it is, one can also denote it using, let's say, mu m, if you are getting confused with the previous one. But in this lecture and all the upcoming lectures also, whenever I'm saying mu, it denotes the magnetic moment. I'll be specific if I'll be saying something regarding to the dielectric one. So the unit of the magnetic moment mu will be ampere meter squared. Okay, so A stands for ampere meter squared. Okay, so now we know the basic origin of the magnetic moment is the charge, the electric charge motion. All right, but in a, for example, in an atom, the charge motion can occur via three reasons. First, the first would be the electron orbiting the nucleus. Okay, electron orbiting the nucleus. So this, you can also say that the orbital angular momentum of electrons. Orbital angular momentum of electrons. All right. And if I need to denote it, I can say something like, let's say our electron is going like this, then this side would be North Pole and the remaining would be this side, South Pole. Okay, all right, so this is, let's say, the orbital motion when the electron is orbiting around the nucleus. The second would be the electron spin, because electron, it's not just a spinning around this nucleus, this electron is spinning around its own axis as well. So which gives you the electron spin. So the second one is electron spin, and we can say that it's the spin angular momentum of electron. Electron. Okay. Third one can be the nuclear spin, similar like the electron, the nuclear spin, but in general the contribution would be small, right, compared to the electron, because nuclei is pretty heavy compared to the mass. So the third one is the nuclear spin. Okay, and I'll just write it down. Small contribution in general. Okay, so these are the three motions which are possible in an atom. So I think except for pretty limited case, most of the time it's the electron motion, meaning the spin, and the orbital motion of electron, which is responsible for the magnetic behavior. And you can compare this motion with the motion of Earth that spins around its own axis, while simultaneously having an orbit around the sun, right? So it has both kind of orbital as well as spin motion. So that's why these electrons, they create spin magnetic moment, and they also create orbital magnetic moment. All right. So as I said here, if the electron is going around the nuclei in an orbit, that will give you orbital angular momentum. However, electron is spinning around its own axis will give you the um, spin angular momentum. Or here I should draw the nuclei such that it's around the nucleus. Okay, so this is how this is the orbital motion, the first one, and the second one is the spin motion. Okay, so in the beginning, I think Niels Bohr was the first who considered that magnetic behavior of an atom, it's based on, I mean, he just took the idea from the planetary motion and he said it's the responsible factor is the orbital motion. But later, we know that spin magnetic moment plays really crucial role in determining the magnetic property of the material. So before it was just orbital, which people consider, but later the orbital and spin now both we put on equal footing. So let us now describe the proper form of orbital magnetic moment when, let's say, the orbital angular momentum of an electron is given. So if we have a charged particle rotating in an orbit, this creates mu, which is angular magnetic moment. And the formula is given by Q times L divided by 2m. So what is Q? Q is the charge of the particle. L is the angular momentum. M is the mass of the electron, the charged particle, whatever it is. Okay, so this is the formula for the magnetic moment, angular magnetic moment. And we also know that for if, let's say, the radius of the rotation of the orbit is r and m is the mass and v is the velocity of the charged particle, then L is equal to mvr, right? This is the radius, this is the velocity, radius of the orbit. Okay, and Bohr also showed that the angular momentum of the electron is quantized, right? The electron around the nuclei, it rotates in a quantized orbit, and there is a basic unit of magnetic moment also, which is generally defined, and we call it, let me just say, the basic unit of magnetic moment, because you will hear this term quite a lot whenever we talk about the um, whenever we talk about the magnetic materials. So the basic unit of magnetic moment is something called Bohr magnetron, and we denote it using mu B, capital B because of the Bohr. and it's form, let's say the form of mu b, it's just h divided by 2 pi times qe divided by 2m. Let me write e because it's all defined for the electron. So QE is the electronic charge, ME is the electronic charge, and ME is the mass of the electron, and H is of course Planck's constant. So if we put down the values of QE, ME, so this mu b, one can calculate, it's 9.274 into 10 to the power minus 24, and the unit will be ampere meter square. You remember in the beginning I said that it's the unit is current times the area, so that's why ampere meter square. Okay, so there's another one, just one more parameter which we'll be using. So it is called the gyromagnetic ratio. So gyromagnetic ratio, which is denoted as gamma, and we write it down. So gamma is equal to q divided by 2m. Okay, so we most of the time again we use, let's say, q is equal to qe and m is equal to me. Okay, so this is more or less the origin of the magnetic moment, and it's the electronic motion, charge motion, whether it's in the orbit or it's in the spin. And generally the nuclear one is way smaller compared to the electron one, so that's why we consider only the orbital and spin part of the electron. Okay, similarly, as I just discussed, let's say the orbital magnetic moment, one can also define, let's say, the mu s, which will be spin angular momentum, and I can just say that E by m times s, so where s is spin angular momentum. Okay. One thing which I forgot to mention about the Bohr magnetron. So we define Bohr magnetron as a unit of magnetic moment, right? Just here, mu b. This gives us, or it allows us to express the magnetic moment of whether it's ion or atom or molecule. Okay, so meaning the unit that will say, let's say something, the magnetic moment is 5 Bohr magnetron or 10 Bohr magnetron, and so on, depending upon how many number of unpaired spin we have. I'll just give you an example how to calculate that. But just before this, the total is, right now I define what is magnetic dipole moment. But if we define, let's say, something called total magnetic dipole moment per unit volume, that is called the magnetization, capital M. So it's similar to your the polarization, capital P, that we saw in dielectric. So that was the total dipole moment, electric dipole moment per unit volume was P. So now I can also define the magnetization, which will denote as capital M, and its definition will be total magnetic dipole moment per unit volume. And if, let's say, one asks you to calculate the magnetization of the material, so we need to do the vector sum. It's a vector quantity like the polarization. So we need to do the vector sum of different magnetization of electrons and nuclei that constitutes the atom. Okay, so that's how the magnetization will be calculated, and the unit of the unit of m. So the dipole moment is ampere per square, sorry, ampere square meter, right? I times A. So it's ampere meter square is our magnetic dipole moment. Divide by volume, which will be meter cube. So unit will be ampere per meter. All right. So I'll just say it's something like this. Okay. So this is how the magnetization will be defined. Apart from that, just to give you an estimate why we are, in general, we ignore the nuclear spin part. See, nucleus, it doesn't have the planetary motion, right? It doesn't have an orbital motion, planetary motion meaning. It only has a spin. And you know the way we have defined mu, it's inversely proportional to the mass m. So if it's electron, it's mass of the electron. If it's nuclei, it's the mass of the nuclei. And the difference in mass between the nuclei and electron, it's of the order of 1000, right? So nuclei is 1000 times heavier than the electron. So that's why the magnetic moment, so I can give it a star. So magnetic moment of nuclear spin will be almost 10 to the power minus 3, 1000 times smaller, because the mass is 1000 times larger than the electron one. Okay, so it's 10 to the power minus 3 mu b. So that's why it can be ignored. Compared to the electron one. All right. And where it will be ignored, when we'll be calculating the total magnetic moment of the atom, when we will calculate the total magnetic moment, the total mu of an atom or an ion. But there are some important application also which people use in NMR, nuclear magnetic resonance, or MRI, magnetic resonance imaging. But that's beyond the scope of what we are going to learn in these lectures. Okay, so there will be some specific courses and chapters in the higher in the higher classes. So that's why I'm not going into those ones. But just keep in mind that nuclear spin is also important in NMR or in MRI. Okay, so now to calculate the total magnetic moment of the atom, as I said that we'll just ignore, let's say, the nuclear part. So we just need to add all the magnetic moments of the electron. All right. And for the electron, we need to consider both angular as well as spin. So now I think, because I'm repeating it so many times, it will be clear to you that there are two parts. Most of the times you might have seen in your quantum mechanics background or quantum mechanics subject that whenever we talk about angular momentum, we say that it's denoted by J, and it's the sum of L plus S, the angular plus the spin part. Here I'm just going to give you an example. For example, let's say manganese. And manganese has the atomic number Z is equal to 25. Okay, and we will try to calculate using its electronic configuration what is the magnetic moment that the free manganese atom will have. Remember, when I say free, meaning there is no charge, meaning just one single atom. Okay, because in most of the time, if you, let's say, make a crystal out of the manganese atoms, the net magnetic moment will be zero, because it just cancels each other. All right. Similarly, if there is some other compound also, however, the individual atom, it will have some magnetic moment, but the overall effect the net magnetic moment may result into zero. Okay, because most of the time it happens that the spin and orbital magnetic moment, they get cancelled out. So the outcome is zero net magnetic moment. But for individual one, there is always, or most of the time, there is an magnetic moment associated. So if I'll write the electronic configuration of manganese, it will be 1s2, 2s2, 2p6, 3s2, 3p6, and before filling, in general it's 4s2, 3d5, right? Before filling D, we always fill the 4s1. Okay, so if you will see, it's from 1s till here, the orbits are completely filled. S can accommodate only 2, P can accommodate 6, and so that's why. But if you see the last one, which is the d orbital, so d orbital is half filled. So there are 5 unpaired electrons. Okay, so because of these, and most the important thing, in all those 5 electrons, the spin 1, 2, 3, 4, 5, the spin will be in the same direction because the system wants to minimize its energy. Okay, so it's half filled orbital, half filled d shell. And now, so you can say that because of these 5 unpaired electron, which are in the same angular spin angular momentum, so spin of each unpaired electron, we just have to sum it over. Or there is a nice formula also if you want to calculate mu. It's actually n into n plus 2 Bohr magnetron, which is, let's say for us, the number of unpaired electrons are 5. So 5 into 7 mu v. So square root 37, I don't know, whatever it is. So the answer will be this. Okay. So this is, let's say, the magnetic moment of the manganese. Similarly, if there are some ions, it's in some other state. So you need to calculate the electronic structure and see how many unpaired electrons are there. Okay. All right. So this is how one, in general, calculates the magnetic moment. And you can ask what happened to the orbital one. So in the orbital one, actually all these 5 electrons, they just cancel each other. All right, because for D, the orbital moment will go, let's say, plus minus 2, and it just cancels for all. The overall effect is 0. So it's just this spin one. All right, so this is how you will calculate in whenever you come across any atom or ion. But as I said before also, if it's forming a crystal, then the situation can be different, because the magnetic moment, it get cancel out. The overall, the average effect could be 0 or non-zero, depending upon the system. Okay, so this was the magnetic moment part, and I also introduced the magnetization M. Now I want you to just, we'll discuss all these, the type of magnetic material in great detail, but just to see or to understand from the spin point of view, let's say if somewhere, if you see the spins are randomly oriented, I'm just showing here in 1D, but you can have these things in 2D, 3D, and so on. So something like this. So this kind of thing is called paramagnet. Okay, there is no net magnetic moment at all. Then there is another category when, let's say, spins are pointing in one direction. So this is called, so it's parallel. So it's called ferromagnet. Like previously we had paraelectric, ferroelectric, it's in the similar way. The fourth one you can think of when, let's say, one spin is up, one spin is down, and so on. So this kind of thing is called antiferromagnet. Then there is a last one where you have two sublattices. So generally what happens that the strength of one of the, let's say it's this, I can say, I can just put this strength just to show that it's different by a small arrow. So these kind of thing are called ferrimagnets. We'll see these properties in great detail later, but because now we are discussing the unpaired electrons, so how to visualize the different categories, I'm telling you. So one is paramagnet, all random. Ferromagnet, we have spins pointing in one direction. Antiferromagnet, we have alternate up down thing. And the last one is ferrimagnet, where we have alternate one down, but the strength is different. In antiferromagnet, the strength was same. Okay, so this is one thing. Now I also want to, let's say, from the beginning onwards, I'm telling you that dielectric and magnetic material, they are really all quantities and qualities are pretty much similar. So that's why I want to correlate those two things. Then, for example, let's say in the electric part, what we saw, and magnetic part, what we have seen or what we will see. Okay, so in the electric field case, we have electric field as the cause. Okay, we were denoting it using E. In the magnetic materials, we'll have magnetization or magnetizing field, not magnetization, and this will be denoted by H. Okay, so these two are the cause in the respective materials. In the electric one, the effect was polarization, and we denoted it using P. In the magnetic one, the effect is just before this I discussed, which was magnetization, and we denoted it using M, right? Magnetic dipole moment per unit volume, or in the electric case, electric dipole moment per unit volume. Similarly, here in the electric case, we had dielectric displacement, and we denoted it using capital D. In the magnetic case, we will have something called magnetic induction or flux density. It's the same thing, and we will denote it using the symbol B. All right, so these are the, let's say, first, second, third. Now the fourth one is the susceptibility. So dielectric case, it was dielectric susceptibility. And we denoted it using chi E. For the magnetic case, of course, it's magnetic susceptibility, and we will denote it using chi M. So E and M, it just distinguishes whether we are in electric one or in the magnetic one. The next quantity is dielectric constant. So there we denoted it using K, or relative permittivity also we said, so it was epsilon R, right? So here we will call it, in the magnetic case, we'll call it relative magnetic permeability. There it was permittivity, right? This epsilon. Here it's permeability. So let me just write it, relative magnetic permeability. And we'll denote it using mu R. This R is for the relative one, like the epsilon R. Okay, apart from that, as I said, we had here ferroelectric, paraelectric, and ferri, and so on. So similarly here we'll have ferromagnetic or paramagnetic and so on. Okay, so these are, and also I think I introduced a concept of piezoelectricity also. So here we'll have something similar, piezomagnetism. So let me just write that also, such that I cover most of the things. If I'll forget anything, I'll come back later. Piezoelectricity in the electric case. Here we'll have piezomagnetism. Okay, so these are more or less, I think, the full list. And things go hand in hand. There we had the cause, the effect, the displacement. Here we'll have, I'll introduce the density. These I think till now we have introduced only M. Actually, I need to introduce all the other quantities, H, B, chi, M, nu, R. So we'll see them one by one. But just remember, the applied magnetic field is the cause, okay? And the magnetization that is being created, it's the effect, like the polarization. Okay, so let me just say that, let me just introduce the magnetizing field. So magnetizing field meaning the thing that we apply externally to the material. So applied externally to the material, and it is denoted as capital H. Okay, and it creates, I'll just write in the bracket, this is the effect. Nope, sorry, this is the cause. So this is the cause, and the effect, it creates M, the magnetization. Okay, so same way. So now what is, let's say the third quantity, which was magnetic flux density or magnetic induction. So it's basically the there will be certain number of magnetic flux line per unit area, right? So the number of flux line per unit area is known as magnetic flux density or magnetic induction. So magnetic induction, or we'll say the flux density, and we'll denote it using V. That's the number of flux lines per unit area. So this is called the B, and the unit of flux density is Weber per meter square. Okay, so I can also denote it WB divided by M square. It's the same one. And this is also equivalent to what we generally call Tesla. This I'm pretty sure you have heard of. Okay, and this thing is pretty much equivalent to the dielectric displacement that we saw in the dielectric material. So till now the H, actually in general the magnetizing the H, the magnetizing field or the magnetic induction, they are sometimes vaguely there, you just call them magnetic field, okay? And they both play the role of electric field. However, there is a subtle difference that which will become clear, that there is this permeability that appears in the relation between B and H. Okay, So that's why I'm just calling them H and B, but sometimes you will see in most of the books, meaning when, let's say, in Maxwell's equation, so the H or B plays the role of the electric field. So I don't want to create unnecessary confusion, but just you should keep in mind that there is a factor which is involved. Otherwise, B is proportional to H, or other way around, H is proportional to B, but there is this permeability factor that we'll see. All right, so this is more or less the comparison between dielectric and the magnetic material. One can also ask a question that how we generally create the magnetizing field. Okay, so let's say I'll just write down how to create magnetizing field H. All right, so generally it's created by passing a current through a wire. Okay, we know that if there is a current, there is a magnetic field. So what is the basic structure generally which is used? It's either a toroidal solenoid or a solenoid made up from an insulating conducting wire wrapped around a cylinder. So let me just quickly draw how it looks like. So let's say a toroidal solenoid. So as the name suggests, it is something like this. Okay, so this is my toroid, and here let's say it's the current. This is I. So here are the different loops the wire is going around. Okay, so there are plenty. I mean, I'm showing this because of my drawing, but there are plenty of winding going around. Okay, so let's say I is coming from this way and here. So this is our toroidal solenoid. The other example that I just said, that solenoid made using a current carrying coil. So solenoid using a current carrying coil. So I just need to draw a cylindrical kind of geometry. Let's say here the current is coming. It's something like this, and we have wires which is going around. Okay, so this is the another geometry, or another which we will use to generate the uniform magnetizing field. All right, so I can denote, let's say, consider a coil of length L, small l, with n turns. All right, so the magnetizing field H is defined as capital N times I. So what is capital N? Capital N is N divided by L. So the number of turn per unit length. All right, so that is called the magnetizing field, and the unit of H, the magnetizing field is amperes per meter, or one can say am, because the meter will come from this L over here. It's N times I, right? So that's why ampere meter. Okay, so this is the way we'll define the magnetizing field in the system.